would it be possible that taxi drivers who spent at least 8 hours and probably more per day finding their way around a very complex environment would actually, through time, change the structure of their brain?
Older adults are demanding more and more of themselves. So this incredible demand that we're seeing from the older population in maintaining their cognitive abilities places a burden on science to understand what we can do to maintain these critical and fine-tuned cognitive abilities. We're beginning to understand that the ability to maintain these processes is dependent upon how much you're using them.
The function of the visual system is to extract information from the environment using the pattern of light that falls on the retina. And people often ask about the fact that vision is piecemeal and it uses tricks. All of those observations are a reflection of the fact that the whole function of the visual system is to extract information.
Our brain is an extraordinarily powerful filter and integrator of all the information that we get through the outside world.
Every moment of our lives, we make decisions based on information derived from our senses. This information gives us the cues that we need to survive and thrive. But what if we could do something to dramatically impact these abilities? What if we harnessed the tools of neuroplasticity that we have at our disposal? What if the brain ultimately holds the key to our independence? Join me as we explore the possibilities and future of brain fitness, sight and sound. The transformative power of the brain is predicated on the principles of neuroplasticity, the ability of the brain to change and adapt as we age.
I once had a stand-up fight with a very eminent neuroscientist in public about plasticity, because his definition of plasticity was just that thing of growing little new synapses, little new connections between nerve cells. And my definition of plasticity is much wider. It's any change in brain functional structure that results from interaction with the environment. And that can include mechanisms that are structural, like new synapses, new nerve cells, strengthening of synapses, but essentially, to my mind, best defined as something very general that gives you an input into this idea of the brain being a very dynamic piece of machinery, quite unlike any machine that we know, which is able to respond in a very dynamic way to the environment and express itself through our bodies.
Within our head, we have the capacity in our brain to change it. We have the capacity to improve it. We have the capacity to strengthen and refine it. In vision, in our operations, and then we have the capacity to improve it as listeners so that our listening can be refined. And the cumulative consequence of all of this is a substantially greater potential to have a richer, sustained, safer, and more likely independent older life.
Having a clear view of our world is largely dependent on our ability to get good information from our senses: taste, touch, smell, hearing, and vision. It's simple to think about seeing and hearing as a function of just the eyes and ears, but those sense organs are a mere fraction of the whole story.
The eye really is shaped like a ball. It's truly an eyeball, and what you can see is sort of the front of that ball. The colored part that you see is called the iris. The black part is the pupil. That actually isn't a thing, it's just a hole in the middle of the muscle. Between the very surface of the eye and the iris is something called the anterior chamber, which is just fluid filled. Behind the iris is a whole bunch more fluid called the vitreous fluid. And then at the very back of that is the retina. The retina is a layered structure which is set up so that the cells that you actually see with are in the front, but the light has to go all the way through to the back to change these pigment-containing cells, which then send a message to the cells in the front. That message then goes all the way back again through a sort of hole in the back of the eye called the optic disc. And all the fibers from those cells join together to form the optic nerve. The number of fibers and the number of cells that are dedicated to vision is extraordinary. If you just take your optic nerve, which really has all the information you use for vision in it, and dissect it out into all its individual fibers, there's about 1 million fibers in there.
Receptor cells in our sense organs encode information and relay it to the brain. These signals are refined in their transmission to the cortex. And there, the information is decoded for use in the control of action and thought.
And the cortex is really where I think the interesting part of the brain is. In the back you have your occipital lobes, which is where your visual cortex is, and then wraps, like little arms, are the temporal lobes, and that's usually where your auditory cortex is, where you experience hearing.
The higher parts of the brain associated with thinking, learning, and memory. Approximately half of that is actually devoted to processing what we see. Whenever there's any ambiguity in what we see relative to what we hear, or even what we smell or feel relative to what we see, we always go with vision. It's our dominant sense.
The point of it is that you see with the brain that's in the back of your head. So in sense, I guess you have eyes in the back of your head.
So once information from the eyes received by the back of the brain, the visual cortex, the information is split off into two components, the what and the where system. And in order to see a visual information or a visual scene, you need to know both where things are in space and whether they're moving, as well as identify what they are. And so there are two distinct processing streams in the brain that handle these things, but there are interconnections between them so that you can link them back up. So if you see a ball moving in space, you can both identify that it's a ball and where it is in space.
We have, in a sense, two visual systems. One of them is evolutionarily old. We share it with other mammals, and it doesn't see color. It really isn't sensitive to difference in color. It mostly sees the world in black and white. And this part of our visual system is important for navigating through the environment, spatial organization, depth, distance, motion, and then our object recognition system, the part of our visual system for seeing faces, for seeing color, for recognizing objects in much finer detail, that system is very sensitive to color.
The eye basically delivers information in a highly resolved form in the brain in time and in place, in color. And we take in that information in the brain and we create, of course, the reconstructions of it in all of its complexity. So if you think of something like a painting that is full of complex color, we see all of the detail. We see all of the color in appropriate position in relation to the detail. Instead of a painting, a complex moving scene, we have an amazing ability to see many aspects of that, of what's there, and how it's moving in relation to another. We have all of this beautiful ability to take in this information and make our world out of it.
We're interested in contrast because that's where everything is happening. Local contrast, spatial as well as temporal contrast. We're interested when something appears that wasn't there. We're interested if there's a discontinuity in the image. And we do it by lateral inhibition, a simple circuit where you have one cell and a next cell, and this one inhibits that cell. The visual system, the brain in general, is a binary computer. Cells either fire or not. They're either excited or not, and inhibition can cancel excitation. And so you've got these very simple little elements to work with. And that's what's fun about neurobiology and physiology in general, is figuring out how you can get these complex response patterns from these really simple circuit elements.
And when you think about the task for the visual system, you immediately are led to the view that if the visual system didn't change throughout our lifetime, it really wouldn't work very well. The yellowing of the lens increases as we get older. Less and less short wavelength or blue light reaches the back of the eye. If we weren't able to readjust